As we're analyzing trusses, there's this kind of a special case that we often see inside of these trusses, which is that not every single member inside a truss is bearing some of the load. Some members have no load whatsoever, and we call these zero force members, which is pretty intuitive because there's no force going through them. So what we want to do is identify these zero force members really early before we even start solving the truss, because this is going to save us a lot of time, right? We don't want to have to do math if that math is just going to work out to be zero. That would be a giant waste of our time. So there are two really basic rules that we can follow to try to find these zero force members before we have to go and do all the math, right? We don't want to have to do that math if we don't have to. So these are the two general conditions that will lead to a zero force member, which condition A here is this idea that two non-collinear members, so two members that don't fall on the same line, intersect at a joint with no load. So two members coming together and a load is applied to neither of them. And an example of this would be this truss that's right above my point A here. This truss members AB and BD intersect and no load is being applied to either member. So these two members bear no load. They are zero force members. This truss would operate exactly the same without them. No load on them whatsoever. And again in this truss, we can see CE and CF are two members that intersect, and there is no load on this joint between them, no load on this joint E here. And because of that, both of them are going to be zero force members. So immediately we can kind of eliminate them from our math and from our thinking about this truss. Really, they're there for stability, and in case a load ever was applied to, say, point B, we would want the members there so they could take on that load. But in its current state, this truss as is does not need them. They are zero force members. They take on none of the load of the truss. So this is the first condition that can be met. Two non-collinear members intersecting at a joint with no load. So the joint is what has no load between them. The other condition is this condition B over here, which is two collinear members, so two members that fall along the same line, and a third member tries to intersect them, and there's no load at that joint. So an example would be this truss over here at the far left. If I look along this line from B to E, every member here, BC and DC, are collinear, right? BC, this member here, BC is collinear, falls right in line with CD, which means that AC that tries to intersect them there is a zero force member. Now this would not be true if there were some load, 5 newtons, applied at point C, then that would not be true. But because there is no load on point C, AC is a zero force member. And by that exact same logic, since CD, that's an eraser. Since CD and DE are collinear, they fall on the same line, AD is also a zero force member. So in this truss, it can really be simplified to just a triangle. Right? Just the triangle from A to B to E. Because the load is only being applied at point B. No load applied at C or D. So those are zero force members. Again, this makes it way easier to solve a truss if I can eliminate almost half of the truss because they aren't bearing any load. So let's look at a couple of these other ones, right? If I look at this truss here, do I have any zero force members? Now, you might be tempted to say that this BD is a zero force member because it intersects this from D to C and A to D. But there is a load here. There is a load. P2 is loaded on point D here. And because it is loaded, there are actually no zero force members in this truss. Every member is bearing some of the load, right? B is connected to a pin, C is connected to a roller, D has a load on it, and A has a load on it. Everything has a load. Every member of this truss is going to be load bearing. So this has no zero force members. But what about this last truss? Right? Typically when you're analyzing these, you want to find the easiest ones first, which to me are looking for those straight line members where a member tries to bisect it, but it really doesn't need to because it's not going to be bearing any load. So in this example, this last truss here is, I can see from H to G and G to F, they are collinear, and CG tries to bisect them, but it's not bearing any load. There's no load at point G, so CG is going to be a zero force member. Same exact concept, D to E, C to D. DF tries to bisect, zero force member, right? It's collinear. A third member tries to intersect, but there's no load. Then there's no load on DF. And because there is no load on DF, we can also say, all right, if I know there's no load on DF, there's also no load on CF, right? Because now I have GF and EF. No load in DF means no load in CF, right? So in this truss, I have 3 zero force members. Note again, BH is not a zero force member because there's a load applied to B, but I end up with 3 zero force members. Let's take a look at one more example. So for this example, we have a really big truss, something that would be probably pretty painful to find all of the forces in every member for every single member of this truss. So what we're going to do is to identify all of the zero force members. So go ahead and pause the video and see how many you can identify on your own, and then we'll talk about it together. So let's talk about the zero force members that we see in this truss. And if I just start from the left-hand side and I look, and immediately I come across joint C. At joint C, I've got those 2 members AC and CE meeting at joint C, and BC trying to intersect, but it's not going to be bearing any force because there's no load at point C. So BC is going to be a zero force member. And because BC is a zero force member, BE is then going to be a zero force member because all that is bearing force at joint B is AB and BD. So BC, or BE, is going to be a zero force member. And then again, by that logic, if BE is 0, DE must be 0, since it's intersecting. It would be the third member intersecting CE and CG. So it has to be a zero force member. But notice, as soon as we get to DG, you might be tempted to say it's a zero force member, but there is that 4 kip load at point D. So because of that 4 kip load, DG is going to be load bearing. It's not a zero force member. So that's about as far as we go on the left side, and then we come a little more towards the center. We can see at point G, there's too much going on. At joint F, there's too much going on. But we get to joint H, and we see 2 non-collinear members intersecting at joint H with no load. So from F to H and H to I are going to be 0 load members, zero force members. Both of those are zero force members. And then I keep walking on down and looking through my joints. Again, now as I go down a little farther, I see from I to J, at joint J, GJ and JL, collinear. IJ tries to intersect them, but it is a zero force member. So that's zero force, and then I keep walking on down the line. I see there are too many forces going on at I, K, L, M, N, O, P. But at Q, now I've got another 2 members and no load. 2 non-collinear members and no load, so OQ and QR are both zero force members. Again, we're not going to be dealing with any trusses that are this complicated to be solving, but you can see how it's helpful to eliminate a lot of members that we aren't going to have to do the math for now because we know that there is no force. They are zero force members. So a lot of times in these truss problems, it'll ask you to identify the forces in every member and identify the zero force members. So list them out by name. Generally, we just call them their letter names by the ends of the members: BC, BE, DE, FH, HI, IJ, OQ, and QR. Those are the zero force members. So oftentimes it'll ask you to identify those while you're also finding what the force is in all of the other members.